Okay, so good evening. Uh, hmm, let's start today's session. So we are going to solve some questions like we are doing in previous classes. So let's start with this one. This particular tungsten-based hydride reagent they have given, and in presence of light and epoxide, they want to know the production. Before that, I want to show some photo photographs of metal monohydrate complexes. So it is a dihydride. Two hydride donor is present, but similar mechanism you can expect to happen. And these are some of them I have listed over here. So for this here you can see it is monohydride, and in presence of light, this particular metal hydrogen bond can keep, and here that homolysis can happen, so that you can generate this H dot and a M dot, and then obviously this H dot is available now, and it can it will react with your reagent, and further process will be followed. So this is one of the first ways you can say in presence of light how that metal hydrogen bond can be broken and it can react. So this uh, this one you can see. So here it is kind of reductive elimination, but in presence of light it only happens. So that's why you can think of this kind of thing. So H dot R dot they can combine. It is ultimately a reductive elimination, but it needs light to happen. So, and this one is dissociation of ligand. So here you can see in presence of light, one of the ligand is dissociated from your metal center, but that hydrogen and your alkyl units that are present in the product. So this is one of the another way, or you can say another side product that can be formed by this irradiation of light. Isomerization is obviously there. Here you can see it is hydrogen and your alkyl group is in a fixed relationship, but in presence of light, it can isomerize and give trans isomer. So this is also possible. And this one is they have shown is proton transfer. So this particular proton can be transferred with in presence of base like this, and how that MLCT happens. So metal to ligand trust transfer kind of thing. So that is also one of the process that can happen here. So hydride transfer from metal ligand trust transfer like this. So metal to ligand charge can be transferred. So here you have polarized this particular metal hydrogen bond, and then in presence of acid, it can act as H minus. So here it is acting as H plus, and here it is H minus. So according to your reagent, if you are using base or acid, it can you can vary the property of this particular hydrogen atom. So that's the processes of your photo process actually that can play crucial role for this kind of reaction. So here how things happens is, so the right option is C, because two hydrogens, both of them are eliminated. And here in this particular bond, it's kind of oxidative addition you can think is happening. So combining this way, you can say that's how it is happening. So uh, these particular bonds are broken, so it is reduced and kind of thing, and followed by oxidative addition here, so that you can form this kind of. So that's how this will react, and your option would be. So here, if complete hydride transfer happens, so then you can expect this one, or this one is not possible because carbon-carbon insert between these two bond that tungsten insertion is not possible. and this one is also not. That's how this can occur. So these are the some of the, you can say, examples how this particular reagent is reacting. And here you can see that kind of similar example with normal infin unit and this thing that first in presence of H nu. So this should be eliminated, and here you can see this kind of pi interaction is happening, and this particular bond is formed. So for methanol, so again one of the hydrogen is removing, and one OM unit is inserted. In presence of benzene also, so here you can see again that CH activation can be done using this. So hydrogen is or hydride that anyway how it is removing. So here you can see, okay, this is minus and benzene H is H. So kind of this way you can say. So in that way also similar thing can happen for toluene also. So this same kind of activation. So for toluene, that thing is, so both of the hydrogen can be eliminated, and here you can see that both of them are replaced with this particular uh, aromatic unit. So for toluene, this is possible. For sealants also similar kind of trend is following. So here you can see same kind of thing. Silicon is uh, uh, this particular tungsten silicon bond is forming and hydride is removing, and probably hydrogen it can eliminate as hydrogen gas. In presence of ethar, uh, here you can see that dimer formation happens actually. So one of the hydrogen leaves from the molecule, and it gets dimerized, and this kind of uh, system is the isomers are there, but this is one of the schematic you can say, and this particular dimer is uh, in major amount. And for this case, this kind of, so this is similar to your epoxide, how it is reacting. So in the same way, this particular molecule is reacting in the same way actually, because tungsten is inserting between this carbon sulfur. And for carbon oxygen, so same group element, and it is behaving same. So tungsten is inserting there like same kind of reactivity you can see, and that can be formed. And this is on site only substitution happens because it is so here it is KH activation kind of thing, and here it is CD dividation. Both of the products are observed here. So as it is aromatic, so that's why that stage activation is prominent and can happen. But for this epoxide case, so it is not that much visible because they are sp3. So that's the reason for that. So in presence of this uh, CMS, again we are seeing formation of kind of dimer, heterodimer, because in this side the silicon unit is inserting, and for this unit only hydrogen is only there, no silicon unit is inside. So this is with this kind of tungsten reagent. So even with acids, esters, with that also this reacts, and similar reactivity we can observe. So two units of acid molecule would be inserted like this, and for this one unit of ester. So similar kind of reactivity what we have solved here. So similar kind of thing it is observed. And with this kind of trends also you can explain that this kind of occurrence. This is for this particular reaction. Now coming to your this Schwarz reagent. So question is very much simple. So they just want us to identify this particular Schwarz reagent, and this one is D. So so in zirconium, one of the uh, two cyclopentadiene units should be there, One would be hydrogen and another is so this is your quartz reagent. Then another options are not yet. That's very much simple anyway. But let's discuss about the this particular reagent and how it is used in synthesis and how they are made. With this zirconium fluoride and lithium aluminum hydride, this particular reagents are made actually in synthesis. So with LH and this particular molecule, so equivalence should be maintained because only one chloro group should be removed from your zirconium chloride salt. That's why 1/4 millimole is 0.25 equivalent of LH. And and these are the byproducts. That's fine, but in real practice, so what in crystal structures suggest is it actually exists as this kind of dimeric form. So here you can see this center two electron type banana bond type uh, things are used like B2A6 dibromo sorry uh, B2A6 means that diboline system. So in a similar fashion, this kind of bond exists in this particular quartz reagent. And if we look into this kind of the activities of them and how they are used, so here you have a particular amide. So amide to aldehyde. So this can be done using these diverlages, but also this particular reagent is also used for this particular. So to convert amide to aldehyde, here you are seeing that this particular reagent is used. So in situ that reagent is forming. So this is just just replacement of LiLH4 because there are four hydride donors are there. So to maintain the reactivity of that highly reactive species, so here we have only one hydride. So that control over this particular reaction is higher. So that's why this is used, and in situ you generate this particular unit. And then normal hydride transfer happens, and this particular unit leaves, and you end up with this kind of aldehyde unit. So this is one of the examples of this particular reactivity. So for not only that tertiary amines, so if you have that some secondary amines also you can use that and in THF in this kind of 15 to 30 minutes or here you have seen that 2 minutes to 30 minutes, so very much fast reaction. And in this particular condition also uh, the same reactivity can be achieved. And here you are seeing that various uh, functional group it can be used. So with alkyl aryls in presence of electron donating groups like OMEs or withdrawing esters. So this can be so this can be very much functional group tolerant reagent and you can use them. So another reactivity is alkyne to alkene. This kind of iodo or any halide group, if you want to incorporate in the terminal position, this can be used. So at first, that source reagent is used and followed by that iodine treatment. So this particular so you have so okay. So Kabil, you raised your hand. If you have any question, you can ask. Okay, okay, fine then. So for this mechanism, so, in the previous class, I have discussed this how it is happening. So let me just discuss that once again. Uh, Uh, the reactivity of the alkyne we have already discussed. Wait a minute. Please, open that slide. So, we are discussing here about this reaction we are discussing. So, alkyne to this alkene in terminal position. Iodide or any halogen component you can incorporate using this particular source reagent and use. And if you know the particular mechanism, so here you can see in presence of this reagent and this alkyne at first, if you use two equivalent of this particular reagent, so it got just reduction, you can say. So hydride is over here and zirconium is here. So first reduction followed by second reduction. If you use equivalent, so they are trans to each other for that stability. So that's how this reduction happens. And if you use one equivalent of that, you can end up with this particular reagent. Now, having uh, one negative, here negative charge is there. Now you can use any uh, solvent, any this uh, kind of reagents, HCl, uh, 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 Br2 or this kind of, so all electrophiles you can use. And so here it is sigma minus. So if you use HCl, so it plus it will take and you can have this simple alkene kind of thing. If you use Br2, so this sorts of Br plus, so well, particular bromo unit you can fill it, and if you use kind of iodine, so iodo you can do. And here acetyl chloride is used. That's why this acetyl group is incorporated. So in that way, you can vary this reagent and make different molecules according to your requirements. And for this one is what we are discussing. So with two equivalent of this and with iodine, you can see you can make this kind of molecule. So and they are and this particular first reagent is the main thing that is uh, driving this particular reaction. And for this one, so in the same way it can go, and with carbon monoxide you can insert carbonyl carbonyl group in between these two bonds. So carbonyl bond in this insertion reaction also can be done, followed by protonation or any electrophile source, so that you can make this carbonyl to uh, react with this kind of olefin unit or any fluoroiodo. So according to your thing, you can vary this particular agent. So that's how this particular reaction is happening. So here you are seeing different versions of that. So with this olefin, this intermediate is forming, followed by here they have used this particular NH block. So that's why here, so that was this thing is used. So this is sigma. So this is attacking over this particular cell, and this thing is happening. So that's how this particular unit is incorporated like this. And here, kind of chiral ligands can be used so that you can do chiral reaction means enantiomerically enriched compounds. So this particular ligand is used for that. And for this immune formation, again, this can be used. And here it is catalytic amount with this particular compound. In situ, you are generating this particular unit followed by uh, your reagents so that you can end up with. So again, same example, these two, and you can react olefin and aldehyde also directly in presence of this particular molecule, in presence of light. So this kind of bond formation can be done. So here, so the mechanism would be like here hydride would be forming, and here you have that sulfonium thing. So now this carbon can attack over here and can end up with particular. In the same way, with particular reagent also. So here double bond this and followed by this particular addition over here, and this would be acting as leaving group. So carbon dioxide would be removed, and here you have that. Uh, so for here, this directly attacking this nitrogen. Here sulfonium and kind of elimination. So carbon dioxide is removed, and you have generated now this particular olefin unit and has nitrogen. It's kind of now it you can do protomerization so that you can have this amide. That's how this thing is happening. In presence of this kind of vinyl ethers, so something can be done, and they are seeing that this particular bond can be kept using this. Uh, so uh, that way it can be done. And with this one, so again, kind of deep protection chemistry. So p hydroxy group can be regenerated with the help of kind of. So that's the some of the uses of this particular reagent. And that's how you can make it. So we have discussed these things. So coming to this one. So with chain control catalysis, stereoselectivity of polymerization for a prochiral monomer is uh, primarily governed by. So that's the option, and so one of can you mute your one of your mic is unmuted. Okay, so with this in control catalysis, stereoselectivity of polymerization of kind of prochiral monomer, they are governed by not stereogenic center in your chiral catalysis, but it's governed by that stereogenic centers that are formed after that monomer insertion. So that's how it is actually controlled. So these are not the factors. So you can so for Siglan Lata, how it is happening. So this is one of the example of that chain and control catalysis. So so from here we will discuss that. So now just write this and so for signal data polymerization, so the right option would be this polymerization occur on the that tip side of the catalyst. Obviously, it should be happening. So let's just discuss this that we can understand this particular uh, questions in detail. So uh, this signal and nata, this particular catalyst, so they are named after these two chemists actually. So Carl Ziegler and this Professor Nata. So they developed this powerful tool to polymerize this alpha olefins mainly kind of with highly linearity actually. So in polymerization, we are learning that various types of polymerization can happen, branch type. So that's how that category came, high density polymer, low density polymer. So we have seen that for low density ones, we have this kind of branch thing. So to pneumatic chains, they cannot come to each other in great fashion because their packing is disturbed due to this kind of highly branched thing. So to overcome that, so this can be made using that kind of radical-based polymerization. And to have high density ones, we need highly this kind of non-branched unit. So for that, these people have discovered that and uh, long linear polymer they have successfully able to form with this particular pattern. That's why they have won the Nobel Prize also for the development of this regional nata pattern. So generally two particular metals are used, aluminum and uh, titanium. So these two metals are used for that. And these are organolithium, so they are metallics. So that's fine. Mm. So uh, so these are two combinations of that. So aluminum based reagent and this titanium. TiCl4 or TiCl3 both variants can be used and with different type of aluminum based reagent. So with 20 to 70-degree heat condition in presence of these two reagents, that normal alkene unit can be uh, polymerized and they can generate this long linear form. Uh, and their molecular weight you can achieve up to 10,000 to 20,000. So this much molecular weight can be achieved. So these two are the examples of this propene unit as if you use that this as monomer. There you would generate the chiral center over here. So regarding our this particular first, so stereogenic center formed in the monomer insertion. So when fast insertion happens, uh, here you can see you will be generating one chiral center over here. So that's why this thing is called this chain control catalysis. So in that end point where you have that prochiral center, after addition of this reagent, you are generating that uh, chiral center. Mm. So and one of the major observation is that for this kind of polymerization, majorly we have got isotactic polypropylene. So which we have learned in the first class. So the plasticity, how this depending upon this methyl's orientation in the space, you can decide that plasticity. So majorly isotactic polypropylene would be forming in presence of the uh, titanium and aluminum. And if you use this particular vanadium based reagent, then you would expect to form this kind of thin diatactic unit. So the reason we just will know that some sites. So but here the important thing is that varying this particular reagent, we can control that structure of your chain, and obviously that would dictate that ultimate outcome of your material. That's how you can dictate or decide how you want to form that material. And so so that can be fully dependent upon this variation of this particular reagent, if it is titanium or vanadium. So now we just look into the mechanism. So in general polymerization, previously this only that radical mediated polymerization are done. For that case, what happens is you lose control over this safely, because when you generate radical, so let's say it's your monomer and you have generated uh, any of these two radicals. So usually this should be because it is secondary. Now when you do the addition, so if this happens, only then you would end up with this kind of linearity. here another possibility is Canada this central. Then you would end up with a formation of this kind of unit. So here you are already seeing that branch type thing would be forming if this thing happens. So you lose control over your reactive side because both of them are similarly reactive. So for this one, it can happen. Now let's consider that another critical. Again, for that same, we face the same problem as selectivity. For that, this particular NATA catalysts are very much useful because they are selective. Now here you can see again, if you have this particular radical, it can back over here. So then you would generate this kind of unit. So lots of branching probabilities already there. Now another possibilities of Hakokas is only if this attack happens when you are generating this kind of unit. Then only that linear thing would be found. So here you are seeing that how so probability is very much less because out of four possibilities you are only have this particular this one this this fashion attack. Only if this happens, then only you can generate your linear polymer and ultimately high density one, high density polyethylene. So that's why probability is very low, and this radical polymerization cannot uh, make that kind of compound or that kind of material. Another issue is uh, uh, that polymer that you would be forming with this, you that would be having low molecular weight. Means the polymerization this in that repeating unit would be less because radical the species they are very much reactive and they're prone to get quenched with moisture or any solvent that is present. Mm, That's one of the disadvantages. So with that, you cannot generate this kind of thing. So for that, you need figure it out. High molecular weight and also high density polymer. You can with this thing. So that's how. Now look into the mechanism how it is happening. So with ruthenium's guys sulfate and this aluminum reagent. In titanium, you have this particular potential, and aluminum can donate one of the highly units, which is here. Mine, it can be donated over here, so that you can generate this particular molecule, and followed by one of the fluorine unit is also removing, and it is attaching with this aluminum unit. This kind of reactivity happens at first, so that you can generate this, where you have that vacant site and aluminum having this fluoride. So that's how these things happen. After that, your monomer, which is this protein unit that can this high electron can be donated to your titanium, not this unit, the dark side. First, here you have that second side. So this is the molecular orbital representation you can see. So with dxy and phi, so this kind of donation can be happening uh, because of the orbital symmetry matching. Obviously, that has to be there. And for metal to your monomer unit or olefin. So they are pi dx square y minus y square. This particular unit of your metal can interact with your antimony or pi star. You can say this way. So that can be donated like this. So that's how this particular bond is formed. So synergistic effect is obviously there. That's how this thing is happening. So at first, a electron is donated to your ligand or to your metal. Total electron is donated to your uh, pi. So that's how this thing is happening. And meanwhile, you have this particular transition state. Four-member transition state is there. And ultimately this one of the ethylene unit can be transferred like this on this titanium CH2 this thing can happen. So here we are saying that this one is your chain and control catalysis. Because in this particular center at first titanium is attaching due to obviously two reasons, electronic effect and obviously yeah stereochemical interaction or this particular stereogenic interaction that would be present if this titanium and this secondary this unit is having that bond. So two this have having two advantages. That's why this titanium unit is selectively attaching to your terminal center. So that's why we are calling it chain particular CEC or chain in control. So after each monomer unit that would be reacting, you end up with that this this kind of intermediate where in the terminal position only that titanium atom is attached. So that's why this long chain that linearity can be easily maintained with this condition. So let's see after that what is happening. With transitions after that this bond formation is there like this and this particular unit. Now again you have generated one uh second site over here and it can react with your second monomeric unit and this thing can go on like this. So that's why that repeating unit can be come over here and this particular thing can repeat and this is your propagation step actually. So this one is initiation one and propagation. So that's how this can be repeated over time and you will have this kind of polymeric chain having linearity. Now for termination, so there are three approaches are there for termination you can say. The first one is uh, this kind of beta hydride elimination. So with uh, beta hydride, so this first that acoustic effect would be come into your picture. So the titanium and hydrogen have some interaction, and when this donation titanium to this uh, carbon hydrogen sigma star, this donation is prominent. This particular bond breaks, followed by this particular elimination, so that you have this kind of pi complex, and followed by ultimately this thing where you have the metal hydride and olefin. This is one of the ways how that's in the signal polymerization process your chain or your chain ends or termination step happen. So this is one of the way this beta hydride elimination, and this is the another way. where they have shown that beta elimination with hydrogen transfer to the monomer. So here what you are seeing is here we have already one vacant state, right? If this interaction is not present, then another it can attack with your another monomeric unit, so that you would be having this kind of where is that? Kind of condition state. So before fully making this titanium carbon bond, kind of transition state should be there. Now this beta hydride, not elimination, but this beta hydrogen can react with your monomeric unit, and this can attack over here, followed by this and this. So it is actually attached to your chain. Now here you are seeing that your chain is now free from your ligand, means that uh, polymerization is ended. So that big polymer what you have formed, that is clipped from titanium like this. Linearity is maintained obviously. And another unit what is present now is this isopropyl group, which is attached to your titanium. This is also one of the processes that people have observed for this kind of signal uh, reaction condition. So this is again another way you can. And lastly, you can say that hydrogenation also you can do. If you use hydrogen gas, so lastly this titanium. So this is the solid compound. So in the surface, this can be adsorbed like this and followed by hydrogenation. That also can be done, and what they have shown over here. So with hydrogen molecule, this thing can be done, and uh, this in that way you can do that twin termination. So this is just you can say that uh, reduced version of this particular uh, uh, fast method. So that's how they are connected actually. So if you do hydrogenation over here, also you can end up with same. So that's how termination you can expect to happen in your system for this kind of Ziegler-Natta scheme. Now the question is that reduced liquid. Why we are having this isotactic, this kind of special arrangement, all seen, or you can say that meso units. So dyads. So I'll just discuss. I will discuss little. So for macroscopic property determination, we use this kind of thing. So here in this chain we can identify this kind of two uh, theogenic center, and they make actually this dyad. And now here we can uh, uh, determine the relationship between these two theogenic center, and we can assign the naming of this kind of dyads with the help of these two relationships. So here you can see if you have this kind of system, you can have this sigma plane. So they are meso to each other, means meso relationship is there. That's why it is here. It is called mesodiad. Mesodiad. Again, for this case, same thing. So mesodiad. For isotactic propylene, you have kind of mesodiad, and for thin diatactic, so these two are racemic. So, because if it is R, it is S. So that's why they are. This particular combination is called racemic. And here we have racemic diad. So these diads are called racemic. So with this kind of thing, you can have this uh, uh, we can determine if they are having uh, this kind of particularly ordered rearrangement, or some of them are not ordered. So with this kind of relationship, we can determine that this kind of thing. Now, the reason why it is happening, that can be explained from this condition state. So here we are having this particular four member condition. Now, if we write this in this three-dimensional form, so it would be present like this way. Right. Now, in the 3D, we can see that why it is happening. So, that simplicity depends upon these two relationships. If they are seen, or and that can be governed by the bulkiness of this particular unit. So, when after this one to insertion, how this should be forming, that depends upon if they are cis or if they are trans. So, if these two methyl units are trans like this, so they are obviously going to be more stable one. And if they are cis due to steric effect, they are going to be uh, less stable one. So that's how this is like this way, or yeah, this way or this way. This is fully dependent upon this particular. So sometimes what happens uh, when you use that ligands, like multi-ligands actually, uh, and this kind of uh, thing, where your metal center having large bulkiness, this particular center. So for that kind of cases, that your metal center decrease is this particular coming ethyl group would be your cis person or trans person. Then the thing would be reversed, and this methyl methyl interaction become less prominent to determine that outcome of your this biochemical outcome, because here your metal unit having large electron density of your ligand. So this particular interaction of your metals ligand and this methyl group become so much prominent that this actually overcomes that this methyl methyl interaction. So that's how the reversing means symbiotic rearrangement is happening uh, uh, with having your metal cell. So that's why when you change it from tungsten to vanadium, this difference comes, and you can explain with this particular conditions. So here you are seeing that for your vanadium one, this kind of thing is there. For this kind of cases, that methyl methyl chemistry is prominent compared to your metal methyl this particular inter if it is, let's say, interaction A and it is interaction B, IB is prominent or very much effective compared to your IA, this interaction. So that's why this racemic diets are racemic diet. And when you have that titanium based reagent, then the metals and the can which is present there, that actually dictates for normal cases. So for this kind of cases, titanium fluorocompound, so this kind of thing. Here you are seeing huge bulkiness can be there with titanium. So then this particular interaction is measured compared to this. here IA is very much prominent compared to your IB. So that's why only this meso relationship is present like this way, and they have they are arranged in this kind of format, all seen kind of. That's how it can be maintained. So again, these two observation we have seen. In that way, we can determine that zero chemical will come out. In that way, you can discuss. Now coming to your this molybdenum based theory. So this is regarding your the activity of your this kind of molybdenum species and how they are made. With molybdenum sulfide, pentachloromolybdenum, sorry, this particular unit is reacted with your three equivalents of three uh, cyclopropane units having this sodium in them. So they're that means oxygen, so stabilized by that. So you have this one, and they can react with your particular unit, which contributes for free electron donation. Again, this is also for free. That's how first cyclopentane would be incorporated. Then the second one, and followed by they have reduced it with the uh, it is reacted with your NaBH. So H minus source. So H minus source is there. So they interacted with molybdenum like this way, and you can have this kind of paint structure. And kind of way. So this should be this one. To CPU something like that. They are that's are wrong. So this is the product that will be formed. Obviously, this side product will be with there. So one is dimerization of cyclopropane like this way, followed by initial shot and between 60 minutes. So they are also formed. So when H minus is donated, you will end up with pH 3, and we all know that boron diboron like this way they exist, and you have this between. So coming to these, so you want to know that the what is the type of this particular reaction with tantalum, this methyl and CP start. So methyl CP start. So this particular thing to this. So you want to know the name or the process that is happening for that. So reductive elimination is happening because when you have one departed unit or at one of the units having uh, reduction is happening. So this particular metal center would be this, but it's not happening for this particular case. So not true metathesis is also not happening. Beta elimination is not possible because there is no beta hydrogen there. The only possibility is that your alpha hydrogen that is actually reacting with your metal unit, and this interaction is so strong that you are end up with tantalum hydride and followed by this particular bond. That's how it is called alpha hydride, alpha hydrogen or hydride. They are consequence of this aggressive effect actually. So both alpha or beta that elimination proceed via this agnostic effect or agnostic intermediate. So tantalum for this particular case, I have shown over here with tertiary butyl uh, unit. We can observe that for because for third butyl group we have no beta hydrogen, which was solar methyl. So only left with we are only left this particular alpha hydrogen. So this uh tantalum pentafluoride and this zinc based reagent, if they are reacted maintain in this much low reaction condition, you can have this unit followed by this metal lithium uh, reagent so that you can do this one of the elimination of chloroquine and followed by this thing. So now here you are seeing that uh, alpha hydrogen is eliminated uh, and it is attached with your uh, blood butyl group so that uh, you have this particular unit, and this is one of the way to prepare this particular reagent. And here again that alpha hydrogen elimination is prominent. So if we discuss a bit about this acoustic effect, so we are just we have seen that it is actually three center to electron because the uh, three units that are involved over here are metal, hydrogen, which is connected to your carbon molecule. So this three center to electron bond obviously is the feature for this particular thing. So here the some of the examples of this. So these are the some first structurally characterized beta agonistic metal alkyl compound, and that bond length and bond angles are shown like this way. So if titanium having this phosphorus ligand and this alkene unit, this particular beta hydrogen having interaction with the titanium. And so in crystal structure, they have able to observe this particular thing. There is where you are seeing this kind of geometry is maintained. So here the angle is like close to this 86 degree, and the bond is uh, length is 2.29. So there is some major amount of interaction we can see. Because this titanium carbon bond length is much more higher compared to this one. So for this particular compound only, this thing can be observed. Now let's see this particular titanium or any metal that have if it have more electron and that is donated to your sigma star of this carbon hydrogen, then this particular bond can be cleaved and you can end up with this particular that alpha hydride elimination or beta hydride elimination what we are seeing. So that alpha hydride or beta hydride elimination are the extreme cases of this agonistic interaction. So That's how it can be characterized like in that way because in the middle position, so not that extreme case like hydride elimination. If your system stops in between, then you can call it as this agoristic effect or agoristic metal complex. So these are the possibilities that are there. So what we are discussing. So if you have this particular agoristic alkyl, it can interact like this. So this is the ground state for this. So that's why it can exist in this particular form. But some of the cases, what happens is this hydrogen is completely taken up by that metal. So you have that metal hydride complex like this, and another two are olefins. So this is one of the extreme cases. This is obviously that starting material. If this donation is not at all prominent, then there is no agoristic effect we can say. And if it is in between, it is agoristic complex, and if this thing becomes too much or too effective, then this carbon hydrogen bond actually breaks. And you have that metal hydride and olefin. So that's the relationship you can say between beta hydride elimination, agoristic effect, and normal alkyl. So in that way, we can characterize or categorize these particular three instances. Now, so the examples, some of the examples actually, how they are actually characterized. So they are actually agoristic interaction which are present. So this particular state is level one. So that's why this thing is can be observed with this ruthenium based with for this pH3 ligand. There you can observe this agoristic effect to be present like with molybdenum, and this way again it can be seen with boron that tile unit. There you can see this particular thing. And again, this is kind of same example. So this only this thing is valid. So this is actually some early examples how people have characterized or observed this particular special carbon metal hydrogen interaction. Mm. So one other thing is in this way you can actually characterize or identify that metal hydrogen reaction if they are agoristic or anagoristic. So for agoristic interaction, you have that three center two electron bond, which is the characterized thing in particular differentiation. And for these cases, they are largely electrostatic interaction. So this can be observed uh, with this particular bond length itself. So in the crystal structure, if you have that metal hydrogen bond distance between 2.8 or 2.3, that is agoristic. And for this kind of anagoristic effect, so there that bond lengths are much higher. They varies from 2.3 angstrom to 2.9. For this case here, you are seeing that for this case, it is in the range actually. Just in the borderline, but in the range, just lower than 2.3 angstrom. So that's why it is agoristic. And that bond angle also is a major factor because that MHC bond means your particular thing. This metal hydrogen carbon. This particular bond they are talking about, so it is between 90 to 140 degrees. Here we are seeing that only that 90.4 degrees. So it is in the range, and for this kind of things, it is varies from 110 to 170, much higher bond length, because the bond length is also higher. So so some relaxation over there is obviously with there, because there are long chain like this. And another thing is your proton number. So for agonistic effect, this that delta is, it is in a field region, and for this there downfield region to normal field. So if we have normal state 53 state, uh, from that, if you have agonistic effect, it will be a field region, meaning that minus 5 to minus 50, 15 ppm in this particular range. If you have uh, an agonistic effect, you have downfield region, you do observe that. So that's what they have given here, that linguistic interaction can be detected, the presence of that particular proton NMRP that is shifted from normal aryl or alkane, what you are using, uh, that of a hydride ligand group. If they shift in that upfield region, like minus 5 to minus 50 ppm, in that way, in this particular range, then we can say agonistic. And some coupling value is there. So with this kind of thing also, you can determine or confirm this particular interaction. And switching frequency with IR, so that also can be helpful. So for this agonistic interaction, you would expect to reduce carbon hydrogen stretching frequency, okay, so because uh, in the sigma star, the electron density is donated, so your carbon hydrogen bond is weaker, so the stretching frequency would be lower. This is the simply observation that also can be monitored to confirm this kind of. So this is again one of the example of zirconium salt having agonistic effect. So it is alpha agonistic transition state for protein insertion, and this is some, so gamma agonistic also can be seen for some of the cases like this way. So five-member transition state type thing with written like this way, and that will be gamma agonistic. With rotation, all hydrogen in that these three they can interact, and in that way they have shown. So with two hydrogens itself, there are two agonistic effect is there. Two both of the hydrogen are in this kind of fashion, so that they have some interaction. So this can be seen in here. When you have a particular polyphene unit, so per insertion, so when your metal or catalyst is reacted to your monomeric unit, or you can say the olefin unit, after insertion you have this particular. So this we have seen for Piglanat, right? So this is also one of the consequence for that no branch product formation, right? Because if we have this particular this kind of insertion, only then you have can see that beta hydrogen agonistic effect, and that in that way the system would be stabilized. So that's why in the earlier case I'm saying that both electronic and both steric, both factors are in favor of Wigner catalyst so that it can make you long linear or no branch. So here previously we have discussed why according to that steric reason, but here we are seeing the electronic effect, which is also in favor. Why that only this terminal insertion is happening for this metal. The reason is this agonistic effect. So again, if agonistic effect become much stronger, you can end up with this thing followed by uh, again insertion in the reverse way. So that way, the other things are possible. But the thing that they want to emphasize over here is that that agonistic metal hydrogen carbon involves donation of electron density associated to that carbon hydrogen bond to that metal center having 16 electrons. So your metal having some electron deficiency. To overcome that or to stabilize that particular state, that sigma electrons of that carbon hydrogen is donated to that metal center. Sigma complex is formed like that way, and that is why that agonistic effect is here have said that particular thing only. Uh, so, uh, with that, this agonistic effect is, and this can be supplemented by the back donation. Now, your metal having electron density, and that can be donated to your sigma star of that carbon hydrogen. So again, that's synergistic, uh, which is we have seen for pi complexes, for sigma complexes. Again, it can be seen. So now the issue is if now here what they want to tell is if that particular donation is not much stronger, then you would see no egoistic effect of sigma to metal donation. And but another issue is if that metal electron is uh, very much feasible to be donated in the sigma structure. Here, that interaction. Whereas if that back bonding metal to sigma star is too strong, then that cleavage of sigma uh, carbon hydrogen bond be uh, happening and thereby resulting the formation of alkyl halides. Sorry, not halides, hydride. So this particular thing actually they are describing, if this thing becomes too strong, you would obviously end up with this particular methyl hydride complex, not kind of aggressive. So this donation should not be that much strong and should not, and this donation it should not be that much less. So in some, you can see in the some middle way that should be there. So some balance should be there, so that only you can observe this particular aggressive complex. Coming to our experiment about catalyzed side contact. So for this case, you have the catalyst having some uh, chiral ligand. So then this chiral ligand this actually dictates the this mechanism. So we obviously learn about this mechanism in detail in further classes. For that, and this simply we can explain it like this. So formation of diastereomeric complexes of catalyst with prochiral monomer and rate of the migratory insertion is different for two diastereomeric complexes, obviously. And stereo regularity is governed by that catalyst, only the asymmetric catalyst. So these not true because if we add different phases, means D phase and south phase, then you end up with racemic no selectivity would be there. So it is not. So for this thing, in two way I can explain. So you can just consider uh, normal hydrogenation. Let's say you have your catalyst. So let me first some asymmetric hydrogenation. So that this particular concept would be cleared actually. Let's see if you have this particular chiral ligand. It's bent like this. So you have some chirality here because yes, it is spiral. So this should dictate special rearrangement of coming hydrogen. That's how it can be dictated. So it is chiral. Now if you have any olefin, these are the prochiral phases. So to have if if it attacks from here, it is reface and here it is two different phases. Now we want to do this catalyst site control mechanism, right? So at first, this particular metal will interact with your olefin. So kind of how complex it should be forming. Here you have that pyramid. Means what? Mm, like this way. So when this is attached like this. So hydrogen that is coming. So from refaces would be much more feasible because it is attached like this way. So five phases kind of block. So reface approach is very much material. So you would end up with this kind of compound where hydrogens are oxidized. And so this particular thing is one of the diastereom. So that's what they're calling here. That diastereomeric complex. Here it is chiral and it is prochiral unit. So some of so it is diastereomeric complex. And the other fashion we have, let's say, this is one of the fashion it can interact. And another fashion would be obviously so here chirality is there. It is like this way. So here you are thinking why it cannot be done because let's say here or here some interaction should be there if the tail is in that place. So here this is why we are discussing for if we discuss one particular space then you can decide from where it is coming, but where the concept you just try to understand. So for this formation of this pair is little bit not that much feasible for this case because here you have some interaction as here we have some chirality in the catalyst. So diastereomeric complex formation with prochiral monomer. Uh, so this particular thing uh, is somewhat not feasible. So the side phase approach is blocked like this because formation of this thing is not quite possible. So this particular attack and formation of this particular enantiomer would be in a less amount. That's how that chiral ligand that is present in your catalyst would dictate your final outcome. So formation of that's why these are the right option because formation of diastolic complexes, this thing migratory rate of migratory infection means this thing and this thing. Obviously, this again would be not feasible because having some interaction present, right? So the rate of migratory infection would obviously be different. So that's why it is governing and governed by factory. Obviously governed by only and why it is wrong because two different phases of the method. So if two phases are equally feasible and if you add uh, in two phases, so there is no question of PhD. That's why we have to remove the now. That's why you can explain this. So the ordered microstructure they want to know. So this thing can be explained by that electricity. So for isotactic polymers, we have learned that for isotactic molecules for in this kind of thing. So uh, all substituents of methylene or alkyl groups they are located in the same frame, like this. So this is obviously is one of the ordered structure, and they are having that meso relationship as we have discussed. So 100% meso diet isotactic polymers should be having, and they are called isotactic polymers. When they are called symbiotic, when this kind of racemic thing is there, because they are, if it is R, it is S. So this diets are racemic. So here again, 100% racemic diet are found like this. Above, below. This order is obviously maintained. But if there is no order, so then they call metactic polymers. This it is so that order is not there. Percentage of mesodiads in between 1 to 99%. So if one of the unit is not matched with this particular arrangement like above below, so then we call this having no order arrangement. So we call this as a tactic polymer. So coming to this, so it is now very much easier to understand. So for B, we are seeing racemic diets, racemic. So above below this thing is maintained, and all are meso diets because it is maintained like this way. so that they are racemic. Then it is also mesodiads, so that are maintained like this. So B, C, D, all are ordered. For this case, what we are seeing is if it is racemic, they are then racemic, but here it is meso again racemic. So it is not actually ordered. It's not maintained obviously because here we have seen that when it is called aseptic, that mesodiad is in between 1 to 99 this percentage. So here it is much more than that because racemic diodes are 3, mesodiads are 5 means so here you can see around 40% is there. So that's right, it's not rodent, or we can call it as reptile. It is not correct. This we have discussed the general microstructure of poly characterized by basically proton and 13C. So how? So uh, okay. So when you have a kind of arrangement that makes for arrangement can be actually so for a monomer when you take the proton on NMR, here we are seeing that this particular two proton units, right? This proton and this proton, they are chemically not equivalent. Why? Because particular proton which is above is closer to this methyl group, and, and this particular methyl is closer to that hydrogen, right? And it is far away from methyl. So they are chemically uh, not equivalent. So we would observe this kind of doublet flow. So they would give us different tips. What your this is called isotactic polymer. So each proton NMR we can certainty obviously we can do that with certainty also. Proton and certainty we can observe this. And for let's say now we have seen what that is what happens is highly likely. So, now they are in same environment, right? Because this proton is close to this methyl and this proton is close to this methyl. So they are chemically now equivalent. Right? So for this case, we would just observe one singlet only. So then only we can call as that is thin diode. With photon NMR in this in this uh, uh, easy fashion we can discriminate between these two particular structures. Now, if let's say in your proton NMR, if you have this both doublet and that thing, then we can call the order rearrangement not ordered arrangement is not present. For that, we are seeing both these two kind of thing. Then it is attack. So if we observe this, both of them, it is less affected, it is singlet, it is that affected, it is doublet, it is like that. So if put on an MR itself, we can determine this thing. That's why CD or multi, they are not required for that only. Proton NMR can do the job and since you obviously help to identify which proton is this one because with the experiment we need to confirm that this proton is con- connected to this one. For that certainty would help With this technique only, we can determine that microstructures of your body. So, it's one of the question. So, how many racemic diets are present? So, we know now quite what are the racemic diets if you have this kind of. So, here they have shown that it present methyl group. So, if it is above like this, so we consider it as above, and if it is below, we consider as below. So that's why yeah, so this is the uh, representation, simple representation for polymers, and they in that way it is just described. Now racemic dyads, they want to know uh, how many racemic dyads are present for this polymer. So now let's see how. So if you write this in this kind of chain fashion, so methyl is above, is also above, is below, then above. Obviously, it is a attractive polymer. So here, one, two, three, four, five units. They are there. So it's the whole structure example. And in simple way, this describe like now racemic diets they want to identify. So the racemic diet should be this kind of above below thing. So it is one first racemic diet. This is the second one, and obviously this thing is there. So this is the second. This is third, and this fourth. This is diet. Here itself we can identify that. So this is first racemic diet, second racemic diet, it is third, and fifth. That's why it is the answer is four racemic diets are present. Now say let's say you want to know that uh, mm, meso how much meso diets are present. So in a similar way we can do that counting. So this is first meso diet, second, third, fourth, fifth, and so sixth mesodiaxis. So the percentage also we can uh, here confirm like this. So the diets are present one, two, three, four, seven, eight, nine, and 10. So total 10 diets are there. Four are racemic diets, six are base. So with percentage something. This particular question also came that a percentage of racemic diet or percentage of meso diet. So the simple way you can do that actually. So total 10 diets are present, four are racemic and 41 meso. So in that way we can calculate this. Now today this is our last question. So now if you have any question regarding this today's discussion, you can ask or previous class any doubt you can ask now. Okay, so if not, we can close with this session. So thank you all for joining. So the next class we will continue and the same uh, Friday 6 to 8. So again, thank you all for joining. and we will continue our discussion. So, thank you.